this term beta? Beta is 2 pi over 2. I mean, this argument here, minus j, it could go from 0 to 2 pi, from 2 pi to 4 pi, from 4 pi to 6 pi. Every time you add 2 pi to it, right, really we're winding the clock, aren't we? But when we have beta times this, just listen to me on this and you'll understand. That R value now, a small difference will mean a large difference in beta R, and angularly. You'll see this here in a second, if you bear with me. That's an excellent question. So if you take a look, and his question is this: well, why can't you just make it R up here and right here? Why do we have to put R prime? All right, it'll be e to the j minus j, then beta times, I replace it, it's R minus z cosine of theta, right? If I stuck that in there, right, John? Well, expand that. That's e to the minus j beta r. And then it's going to be times e to the plus j beta z cosine of theta, right? Now, you realize that this could be a value, it could be any value, but when I divide this by 2 pi, I see how many wavelengths away I am, right? Right? If I have beta r, if you think about this, beta r is going to be an angle, right? It could be from 0 to 2 pi, but then if it goes beyond 2 pi, then it goes from 2 pi to 4 pi, or if it goes beyond 4 pi to 6 pi, and so forth, right? But if we want to know how many wavelengths away we are, we could take beta r, whatever that is, and divide by 2 pi. We may have 100, we may have 1,000,000, it doesn't matter. What matters is this, the small difference. I mean, you'll have a given phase right there. This will change a lot over a small distance. And that's the reason you break it into separate things. And we have to integrate over that too. We have to integrate over z, and that's the real reason. So then, now I'm going to go ahead and just show you what happens. And we're going to do this in another piece of paper, if you don't mind. Now I'm going to say that the total E field, and this is for an arbitrarily long dipole on the z-axis. Again, we're talking about a dipole on the z-axis of arbitrary length L that has the current I gave you in the prior one. That E would be equal to the integral of j eta beta, and then I'm going to put the L, or I'm going to put d, not dz, sorry, I'm going to put the 4 pi here. Then I'm going to put I naught, that's the magnitude of I. And then I'll put e to the minus j beta r here. I'll put 1 over r here. And then I'm going to put the last part, I'm going to put e to the j, and it would be beta z cosine of theta. And then it's going to be times the sine of theta, right? Over, or times dz. Wait a second. And that would go from minus L over 2 to L over 2. What I'm trying to do is show you the nature of the integral. We have e to the j beta z cosine of theta dz. You all see that? Now, when you execute this integral, for the sake of time, I'm not going to do it, but it is in your book, and it's a very well-known one. I'm sorry. I had to put one other thing in here, and I didn't. I'm trying to shoehorn this. This would be equal to the sine of beta, right, times L over 2 minus magnitude of z. Remember,
Doc,
that's, yeah.
What page is that on in the book?
That I don't know, but I'll give it to you in 1 second. This is in dipole antennas. He does it with the H field in his book. It's page 448, and he shows you the current. And 449, he gets the H field, but he doesn't give you the E field. I'm going to give the E field. I'm going to give you a treat, believe me. So after you're done with this, this is the thing you take from it. This is an integral. You have sine beta times L over 2 minus magnitude of z here. You have e to the j beta z cosine theta here, and you integrate dz. It's a more difficult integration. But when you're done, you get this, and this you write down. E is equal to, going to be equal to j times 60 over r times e to the minus j beta r. And then it's going to be times something I call small f of theta. And small f of theta will be equal to cosine of beta L over 2 times the cosine, or beta L over 2 times the cosine of theta. Now that's beta L over 2 times cosine of theta. And it's going to be minus cosine of beta L over 2 all over sine of theta. That's what this small f of theta is. And this E field is in the A theta direction. Are you with me? Now that he doesn't give the E field, but he gives you the H field at the bottom of page 450. And if you multiply that by 80, you get what I've got. I prefer the E field. I remember that one all the time. I always go for E field equations if I have a choice. Now, once you have the E field, don't you also have the power density in the far field class? The power density be 1/2 E squared over eta, right? And when you do the power density, oh, I got to tell you one other thing too. Now, I put a small f of theta. What he does is this. He says the power density, this is the average power, or the, oh, this should be power density here. Put down power density in your books. He said the time average power radiated. That's not correct. That's the, using 841 is this is a power density. And here, what he does is take the 1/2 times E squared over eta, or 1/2 eta times his H squared. Either way, it'll get you this. Make sure you put power density down here. That's in watts per meter squared. And it will come down to this. So it's 15, the actual power radiated, P av, will be equal to 15 right here, I naught squared. I naught is the peak of the current, and it's divided by pi r squared. And then he uses f theta. Well, his f theta here, capital F theta, is simply my f theta squared, small f of theta squared. Y'all see that? You have your books, people? If you look in your books, you even look there in 8.47, he just takes the actual small f of theta I have and just squares it. Can you all see that? Now, this is the go-to formula for arbitrarily long straight wire antennas. You get this equation for the E field that I like going to, and this equation for the power. Those are the two. You'll notice that it is a function of angle. This particular function here that you're looking at that's weighing the E field, you don't have a good feel for what that might be. All right? But I'll tell you that it's different. You can do a lot with this thing. There's a lot of weird things that come out of it. What I'm going to tell you is a couple of the most common straight wire antennas, all right, links of them. The first is called the half-wave dipole. How many have heard of half-wave dipole? How many have heard of dipole antennas, straight wires, aerials, right? You've all seen them, right? Short antennas and long. Normally for a lot of ship-to-shore communication, they use HF antennas. They're long straight wire antennas. But we got to talk a little more about this. So if this is the average power right here, and we know the current feeding it, when we integrate the average power over the total sphere, we can get the total power radiated, can't we, class? Now the total power radiated is 1/2 I naught squared times R rad. I want to cut to the chase on this because I'm out of time. Here he goes through it on the top of page 452. He doesn't do it the way I like, but you get the total power radiated right here, and you say it's 1/2 I naught squared R rad. So you can get R rad, and I'm going to just tell you what it is. It's 73.2 ohms for a half-wave dipole, but here he gives it in terms of an arbitrarily long dipole. And remember this guy right here. That's actually that solid angle you have to calculate when you do the normalization. I don't worry about that. This is for an arbitrarily long antenna, and there's a lot of things that come out of it. You can get almost no current flowing in the center if you have exactly a full wavelength. There can be a lot of things happening. We did the directivity. Let me get into the half-wave dipole. And if you don't mind, I know I'm about 4 minutes over. Can you give me a little leeway here? We're going another 5 minutes so I can finish this. I want to show you what I wanted to finish today. So now, when we talk about the half-wave dipole, these are special cases. When L, the length of the dipole, is now lambda over 2. This is extremely common. Here, you're going to have total length lambda over 2. And that means between here and here, it's lambda over 4. Between here and here, lambda over 4. All right, now with that one, what happens is this. Your E field will become J times 60 over R times I naught times E to the minus J beta R. That's as if the arbitrarily long one, all right? But look here. I'm going to use this book as my reference. Remember, for my f of theta, multiplying that, it was this, right? Correct? Now, look at what happens when you have beta L over 2. Well, if L is lambda over 2 here, beta is actually 2 pi over lambda, so it's pi over lambda times lambda over 2, right? And so that would be pi over 2 in here. You can check this. Beta is 2 pi over lambda. L is lambda over 2 divided by 2 will be beta. It's going to be equal to beta. Well, let me do it for you. When I look at beta times
Just
L
be 1/2
over 2, you're going to get beta is going to be 2 pi over lambda, right? You're right. Times lambda over 2. This is pi over 2, or just pi, right? Wait a second. No, I'm sorry. This is going to be this divided by 1/2. So it's pi over 2. You follow me? Beta L, beta is 2 pi over lambda. Lambda over 2 divided by 2 is pi over 2, correct? Now, look over here. That's going to be the multiplier inside this, that cosine. Now, what happens when you do beta L over 2? Well, that's beta L over 2 is pi over 2, right? Well, what's cosine of 90 degrees or cosine of pi over 2?
0.
0. So we get rid of that altogether. And you end up with an E field that just has cosine of pi over 2, cosine of theta over the sine theta. And it's going to be that, and it would be in the A theta direction. Now that's the E field. All right, the power density will still be this guy right here. So the average power density will be equal to 15 I naught squared over pi R squared. And then F is going to be this squared. So it would be the term cosine of pi over 2 cosine of theta over the sine of theta squared. You all see what I'm doing here? That would be the power density. Got me? Can you see it, John?
I see it. Yeah.
This is power, remember. Now, can't we go from power to get E field and from power to get H field very easily if we wanted it? All right, keep that in mind. Now, once you have this, I got to say this. This is the average power density. The normalized power density, just listen to me now. The normalized power density would get rid of all this stuff. And the reason I know this is because the peak value this has is 1. So remember, when you get the normalized power density, you take the peak power density at a given range R and divide it into the actual power density to get the normalized power density. Do y'all remember that? So I'm just going to put it down. P normalized would be equal to cosine of pi over 2 times cosine of theta over the sine of theta squared. Are you with me on that? That's normalized power density. Now, work with me here. Let me finish my thought here. Now, when I go ahead and get the actual directivity max, that would be equal to 4 pi over the solid angle. And I'm not trying to move too fast. And the solid angle would be equal to what? The integral of the P of n right there times the sine of theta, right? Times d theta d phi. Theta would go from 0 to pi. Phi would go from 0 to 2 pi. Do y'all remember that, class?
Mm-hmm.
This was in the last homework assignment.
Like you
And
said,
you,
to not use the omega p,
what?
or is this for?
This is D max.
Yeah, okay. You got. Sorry.
That's calculating the maximum power. I mean, maximum directivity or gain.
Okay.
Now, without doing this, I'm going to tell you, I hate running out of time, but I'm sensitive to your needs too. This comes out to be 1.64 for a half-wave dipole. Please write that down. This is for a half-wave dipole. And the second thing, now once we have we can get the total power radiated. I'm not even going to write that down, but one thing we get when we get total power radiated, we get radiation resistance, don't we, class? Mm-hmm. I'm going to just tell you what it is. For a half-wave dipole, for a lambda over 2 dipole, R radiation, the radiation resistance is equal to 73.2 ohms. And he has that somewhere. This half-wave dipole is on 458. 73.2 ohms is equation 8.84 on page 460. But now I have something else to tell you. Now remember, I told you that antennas have a reactive component that have to do with the magnetic energy or the electric and magnetic energies nearby, right? So normally the actual input impedance on a half-wave dipole, if it's an exact half-wave dipole, is equal to the 73.2 ohms, but then it has a reactive component of about 42.5 ohms. Let me make mention of this 42.5. That will vary somewhat depending on the diameter of the wire used for the antenna. Now, probably as engineers, you can appreciate that. Diameter should make some difference in the actual impedance, and it does in the reactive component. But this is the beautiful thing. Most of the time when they take and say it's a half-wave dipole, it's not really a half-wave dipole. What they do is this. They're going to say if L, the length of the antenna, is 0.485 lambda. So it's not a half wave exactly, it's 0.485 lambda. If this happens, and if and only if this happens, then Zn is strictly 73 ohms. There is no reactive component. Now the reason you like that is because if you have a reactive component, it takes more voltage to get the same current. And remember, the current's the key thing with the radiated power. Are you with me? Can you all understand that? I know I'm going over, but just bear with me. So here's the deal. The antenna electrically looks like this. Your dipole antennas, they have some R rad. That's what you want. That's where the power that's launched
Can you
comes
put your
from.
pad up, please?
Yes, thank you. But you also have this possible reactive component, JX here. You would like to get rid of that because when you have a voltage source here, plus the minus V, and it's driving this, in order to get, remember, it takes current going through here, 1/2 I squared R rad. That's where all the power comes from. The current flowing through here doesn't do beans for us. It doesn't do anything. But that voltage, in order to get the power you want, it'll have to overcome this resistance and that reactance. Got me? So you always have to worry about getting rid of that. And by the way, if you have a J42.5, let me just say this, the typical way to get rid of it is putting a series capacitor right there and just making that capacitor minus J42.5. And that way it gets rid of it. But it's still an added component. And another thing too is, especially if this is a high power device, capacitors can get shorted through if you have high voltages. And that's why you prefer to just have 73 ohms. Okay, everybody on that? We'll pick it up there next time and I'll do a raise. I wanted to get through the half-wave dipole and I did. And I'm gonna give you some homework on this stuff, all right? Now the homework will be far field only. You got me? And you'd be all right with a quiz on Monday that covered this stuff, and I'll answer questions first before I give it to you. All right? Okay? I'm trying to be as fair as I can. I don't want to give you a quiz on material where there's very little or a whole lot. I'm trying to keep them separated. All right, on Monday. So I'm going to give you some homework. We've got a quiz Monday. Any other questions or comments for the good of the group?
So the quiz Monday will be over the half-wave dipole?
It'll be over dipoles. It's really the last two lectures.
Okay.
Because you have to know radiation resistance. It could be short dipole, it could be halfway, but
Gotcha.
frankly, you see the kind of problems I like is where I say, okay, if you want the same results with a short dipole that you had with a loop, a small loop, then how much current? Well, I could ask for the same power or same electric field strength if you had a half-wave dipole. What would you do then? That kind of question. Everybody okay with that?
Yeah.
All right. Any other comments or information for the good of the group? And thanks for that tip about the planes, man. I didn't know that. I got to see what I'm supposed to have said. I can
Did
only
you get the
imagine.
email with the videos?
Yeah, the video links, I appreciate that. Thank you. And if you want to add me to group me, fine. If you don't, fine as well. Just make sure that if there's questions posted, you let me know and I can answer them, okay?
All right, thank you.
Guys, have a great weekend. Stay safe. And any news that is beneficial to us, send it to me, okay, guys?
It'll do.
All right.
Thank you.
All right, have a great weekend. Stay safe, guys. Take care.